So welcome to the last part of lecture 12. In this part here, we want to talk about kind of a quick way to decide whether two vector spaces are isomorphic. And you can do this quickly if both of your vector spaces are finite dimensional. So two finite dimensional vector spaces V and W are isomorphic if and only if their dimensions are the same. So this is a very nice result because sometimes it's very easy to decide whether V and W have the same dimension or not. And from that, you can automatically conclude that V and W are isomorphic. So the advantage of looking at the dimension is you don't have to come up with a linear map from V to W and check that it has all the properties of an isomorphism. It's enough just to look at the size of each of the spaces. And let's quickly go through the proof of this, okay? So let's say that you know that V and W are isomorphic. Well, because they're isomorphic, there's an isomorphism from V to W, okay? But then, by the fundamental theorem of linear maps, the dimension of V has to be the dimension of the null space of T plus the dimension of the range of T. Okay? But now, because T is an isomorphism, since T is an isomorphism, T is injective and surjective. So we're going to think about, well, what does this mean in terms of the null space and the range, right? So the injective part implies that the null space of T is 0, and it implies that the range of T is W. So we have that the dimension of V is equal to the dimension of the null space of T, right? So that's going to be 0 plus the dimension of the range of T, but that's the same thing as the dimension of W because the range of T is W. So that's one direction. And here we're seeing kind of a nice use of the fundamental theorem of linear maps. And we're going to use it, we don't use it in the second part, but that's kind of one of the reasons I like this theorem is it kind of pops up every once in a while and allows us to prove some nice results. Okay, so now we want to go in the reverse direction. We're given that the dimensions are the same, and now we have to cook up an isomorphism. So what we're going to do is we're going to say V1 through Vn and W1 to W1 are bases of V and W. And the dimension hypothesis is being used right here. N and N are the same. Maybe I'll make that clearer here. Same N, since the dimension of W is equal to the dimension of V. This is actually where we're using our hypotheses. And now we need to define a map from our vector space V to W. But remember, we can define a vector space or a linear, we can define a linear map by explaining where our basis elements are set. So I'm going to define my basis linear map by taking the first basis element to the first basis element in W, and taking the second basis element of V and mapping it to the second basis element of W. Okay, and as a consequence, right, we get that this map will take an arbitrary vector, which can be written in terms of its basis, to C1 W1 up to Cn Wn. So this is a linear map. Right? And we're not using anything special here. We're just using this fact that a linear map is defined by where you take your basis elements. Okay, so we have a linear map, and we want to show it's an isomorphism. So it's enough by what we proved earlier to show that our map is both injective and surjective. So it's injective since we're looking at what things get sent to 0. Well, this thing gets sent to 0 if and only if C1 W1 up to Cn Wn is equal to 0, right? Because that's what the left-hand side is equal to. And this happens if and only if C1 up to Cn equals 0, since W1 up to Wn is a basis, right? The only way to write 0 as a linear combination of your basis elements is if all the coefficients are 0. So we know that C1 times V1 up to Cn times Vn is equal to 0. Okay, so it's injective because the only element that gets sent to 0 is 0. Okay, so another way, what we're really doing is just checking that the null space, it contains the 0 element. And why is the map surjective? Well, since for any W in W, W can be expressed as A1 times W1 up to AN times WN for some AI in F because it's a basis. But then you take those exact same coefficients and you look at the vector A1 times the first basis element of V all the way up to AN Vn. This is an element of V, and by the way we've defined our linear map, TV, which is TA1 times T evaluated at A1 times V1 all the way up to AN Vn gets mapped to the vector W. So because T is injective and surjective and is a linear map, it's invertible, so it's an isomorphism, as we claimed. Okay, so this is very nice if you want to decide if two finite dimensional vector spaces are isomorphic, you just have to look at the dimension. So as a nice example of this, for all n, I know that Rn is isomorphic to Pn minus 1R, all the polynomials of degree n minus 1 or less, right? And why is that? Well, that just follows from the fact that both of these spaces have dimension n. So this is saying these two vector spaces are basically the same vector space. All that we're doing is storing the information differently. So today there are kind of two key ideas. Here, let's give myself some more room and make myself pop back up here. So we have two main ideas for today's lecture. We learned about invertible linear maps and we learned about isomorphisms, and kind of one of the nice big results about isomorphisms is if they have the same dimension, they have to be isomorphic. And here's a little comic here about an invertible matrix. They obviously have taken the mirror image. So maybe we'll end off with the joke where here we go. We have our little stick guy and he thinks it's funny. Okay, so I hope you enjoyed today's lecture and I will see you at the next lecture. Have a great day.